Hello students, welcome back. Section 3, Fermat Factorization may be a little bit out of place, but I decided to include it in lesson 9 anyway. After all, that's what our textbook author does as well. The textbook author must have had some reason to group this Fermat Factorization along with Fermat's theorem and Wilson's theorem in the same chapter. So I decided to do the same thing in my notebook too. Fermat Factorization is a kind of opportunistic factorization method applied for odd integers. Factoring an even integer is easy. Just divide by 2 and get reduced as much as possible. And once you hit an odd factor, from that point on, you may have to work out various trial divisions or things like that. One way to do that is to trial division of everything up to square root of n, but this is very, very inefficient method. You have to do a lot of trial divisions. And back in Fermat's time, we're talking about some 1600 something, I think, in 17th century, and division is actually a difficult computation. Square root computation is also a difficult computation. There are algorithms exist, yeah, both for division and square root, but compared with addition, subtraction, and multiplication, those are much harder. And of course, even for today's best computers, if n had been, say, 100-digit number, then this kind of trial division may take some unthinkable amount of time, even for today's best computers. So Fermat considered and proposed some ingenious and opportunistic factorization method, which doesn't always work, but in many cases it worked. And if it works, much better than trial division method, and is based upon these two observations. First, if n can be written as x squared minus y squared, then the factorization is easy. X plus y times x minus y. Now, can we always find this x squared minus y squared form? The answer is yes for odd integers. If you write n as a times b, then you can rewrite it as a plus b over 2 squared and a minus b over 2 squared. Are you comfortable with this computation? Let's see. What is the first complete square? A squared plus 2ab plus b squared over 4. A squared minus 2ab plus b squared over 2 squared. So 4, that's it, isn't it? And then we have cancellation. A squared, b squared, b squared. They go out, and negative becomes positive. So we have 4ab divided by 4. So we do have AB, or excuse me, just AB. So this becomes AB, that's always true. But the problem is, are these integers? The answer is yes, if n is an odd integer, because both a and b must be odd. So a plus b and a minus b are both even. Odd plus odd is even. Odd minus odd is even. So we have integer squared minus integer squared, x squared minus y squared form. So the factorization problem of an odd integer can be reduced to the following Diophantine equation. N is x squared minus y squared, where x and y are integers, or equivalently, x squared minus n is y squared. Fermat proposed this algorithm. First, find the smallest integer such that k squared is greater than or equal to n. Yes, you don't really have to calculate square root. Just get some initial guess, and then k squared is greater than n, k minus 1 squared is less than n. That's what you're looking for. Start from there, and then try x is k, k plus 1, k plus 2, k plus 3, k plus 4, and so on until you get y squared. until you get x squared minus n is actually a square number. And this process cannot go on fruitlessly forever, because eventually it'll have to stop because x cannot exceed n plus 1 over 2. If you do have n plus 1 over 2, then n plus 1 over 2 squared minus n, you get n minus 1 over 2 squared. So if you put that into, so x is n plus 1 over 2, x is n plus 1 over 2, and y is n minus 1 over 2, then x plus y is n, and x minus y is 1. So we end up with trivial factorization n type 1. So if something like this happens, then there's no factorization. So the target odd number is a prime. If it is a composite, then at some point it'll have to hit a square number. X squared minus n is a certain square number. And checking whether given outcome is actually a square number or not, that's going to take a lot of effort, yes. But compared with trial division, it's better according to Fermat's proposition. Of course, this can be effective when this x plus y and x minus y are close nearby, so that if x can be found as k plus something pretty close, not k plus some 5,000 or something, so that humans cannot really handle that much. This kind of factorization method is called Fermat factorization. And let's go with an example problem which Fermat himself worked out. And apparently he must have been proud of this kind of computation, because at Fermat's time, calculating this kind of number and checking whether this is prime or not, or getting a prime factorization of something like this, would have been inconceivable computation. Using those typical prime sieve method, you cannot calculate things like that. But Fermat actually worked out this. Okay, let's go ahead with the solution. And as a matter of fact, Fermat must have worked out number of weeks or even months, maybe years, to get this kind of computation done. Probably not years, but anyway. So I didn't really want to go through with that. It's just traditional method, so I ended up writing a program. So we start from n, and then we have to start from, let's see, smallest integer k, so that k squared is greater than or equal to n, right? So that's the starting number. So I'm starting with the ceiling of square root of n. So integer, the smallest integer, greater than or equal to square root of n. So that's your k value. And, well, according to this, yeah, we have 45,030 is your k value. So let's see. 453030 squared. Yeah, okay, that's greater than this number. 2027651, there's a 700 something. But if you go down 1, now this is less than this. So step 1, getting up to this must have taken some effort, but the algorithms to find square root exist, and certainly in Fermat's time it was known. So he should have been able to get this kind of thing in, well, probably less than an hour. No matter how generously I calculate, probably much shorter than that. And then I'm running this program. So as long as square root of x squared minus n is greater than a floor of that, which means it has some decimal, non-trivial decimal part. That means as long as x squared minus n is not a square number, the square root of that is not an integer. As long as that, just continue next, next, and next. That's what this while loop is talking about. And then when it comes to an end, y is square root of that x squared minus n. And then print x and y. This is what I got. X is 45,041, and then y is 1,020. So starting from 45,030, 45,041, and only 11 steps, only 11 iterations were done. So this is far more efficient compared to calculating the trial division of God knows how many. According to our textbook, yeah, okay, 4,580 trial division. Oh my goodness. So it must have taken some efforts to check those, whether those are square numbers or not. That's trial square root computation, but just 11 trials versus trial division of 4,580. Anyway, we got x and y values, so we can find x plus y and x minus y. They turn out to be 46,061 and 44,021. According to Fermat's computation, we got that. And then you can apply similar trick to this one and that one. Turns out they are both prime numbers. So Fermat obtained this prime factorization. What is this? 2,027,651,281, and got the prime factorization of 46,061 times 44,021. In Fermat's time, this was a very neat, very special achievement. For nowadays computers, this thing may turn out to be nothing at all, but this is big but. If you look at just these numbers Fermat worked out, then if you work out with today's computers, then this is nothing. But then again, if you try to work these out with some 30-digit numbers or 40-digit numbers that today's cryptography problems usually encountered, in that case, today's computers come up with the same kind of trouble that 17th century mathematicians used to encounter. Simple algorithm exists, but cannot calculate it in real time. So what do? 17th century mathematicians use all these kind of neat tricks, very special tricks, opportunistic tricks to reduce so that they can reduce the problem into the range they could calculate. And nowadays, people use exactly the same kind of tricks to bring down the problem so that today's computers can use. So these topics did not die away. They're still alive and well, and they're being applied for computation purpose, even nowadays.